Today we're going to finish up chapter 4. We're going to finish our discussion of apportionment. We're done with methods. We have learned 5 methods of apportionment. So we're done with learning how to apportion. Today we're going to sort of discuss the pros and cons of those 5 methods. What's good about them, what's bad about them. And that will finish up chapter 4. And you will be able then to do all of your project that's due April 5th. Yes?
I just have one question about the project.
Sure.
I did all of them, but when I did the Webster's one, I did like the if and then the number that like California or whatever was.
Yeah.
And then I did like greater than 0.5, like go up, but like.
So for the
0.5,
for the rounding, you did an if-then statement.
But when I did 0.5,
Okay.
like it thought like it's greater than like a half.
Okay.
So it didn't work?
So for Webster's round, so for Jefferson's you use the command round down, right? And for Adams you use the command round up. For Webster's you don't have to write your own if-then statement about how to round. Just use the command round.
Oh, okay.
So rather than round down or round up, the command round uses the 0.5 cutoff.
Oh, it does?
Yeah.
Oh, okay.
So you don't have to use an if-then statement. Yeah. Okay, so like I said, today we're going to dig into some of the drawbacks of each of the 5 methods of apportionment that we've studied. So one of the most basic ways to judge the fairness of an apportionment method is by what we call the quota rule. The quota rule says that an apportionment method should give each state no fewer than its lower quota and no more than its upper quota. So for example, if a state's standard quota, that's their exact fair share, is 138.29, then the only fair thing to do is to give them 138 or 139 seats. If you give fewer than 138, we call that a lower quota violation. And if you give more than 139, we call that an upper quota violation. So think about Hamilton's method, right? Hamilton's method, the very first one we learned, it rounds everybody down to their lower quota, and then some states get 1 more seat, right? Which means they would get their upper quota. So can we ever produce a quota violation with Hamilton's method? No, it's never going to happen. Right. Everybody gets at least their lower quota, and then some states will get their upper quota, depending on how close they are to the next whole number. Okay, but we have 4 other methods here. So Hamilton's methods is good with the quota rule. Let's look at the 4 other methods. So this is an example we've already done where we calculated the apportionment for the Congress of Peridor using Jefferson's method. Okay, so we did this all before. We're not going to do it all out again. I just have the results here. What do you notice about state B's standard quota, their exact fair share, compared to how many seats they actually got? It's too many. They got more than their upper quota, right? The only fair thing to do if your fair share is 138.72 seats is to give you either 138 seats or 139 seats, and we gave them 140. So this is what we call an upper quota violation. Okay, and you notice that the state that got the extra seat, that got more than their upper quota, was the largest population state. And that's not a coincidence. So it turns out that Jefferson's method does sometimes produce upper quota violations, but even worse than sometimes producing these violations is that they consistently favor large states. It tends to be the large states that gets the benefit of getting that upper quota violation. So that's not good. And this problem came to light in 1832. It was one of the most heated apportionment debates in US history. The United States was using Jefferson's method, and New York's standard quota was 38.59 seats, but they were given 40 seats under Jefferson's method. Led to a really heated debate about the constitutionality of Jefferson's method, and that was the last year that Jefferson's method was used. Adams' method and Webster's method were both developed in response to that 1832 failure of Jefferson's method. Yes? Whatever happened to Hamilton's method? Yeah, it was like the first one, and yeah, I don't know. Well, actually, I do know. We're gonna talk about it in a few minutes. Yeah. Okay, so let's look at then we apportioned the Congress of Parador using Adams' method, and let's state B again is the state that has a weird result, right? We have 138.72 as its fair share, but then we gave them 137 seats, which is too few. This is a lower quota violation. And again, it was the very large state that was affected, but this time they were affected in a bad way, right? They ended up having too few seats that made things unfair. So it turns out Adams' method can sometimes produce lower quota violations. But even worse than the fact that you sometimes get these violations is that they favor small states or don't favor, they're anti in favor of big states, right? Big states get hurt by it, so smaller states end up getting favored. So our conclusion is that Adams' method is no better or worse than Jefferson's. It's just biased in a different way. So after considerable debate, the apportionment bill based on Adams' method never passed. So Adams' method was proposed, but then never actually used to apportion the House of Representatives. So let's see if Webster's method is any better here. Looking at comparing standard quotas to the actual number of seats a state got, do we have any quota violations? Any states that got too few or too many seats? No. So we've got no problems here. Every state got either their lower quota or their upper quota. That doesn't make Webster's method perfect. It just happened in this case to not have any violations. It does tend to produce apportionments that are pretty close to the standard quotas. It does occasionally produce quota violations. But they're both upper quota violations and lower quota violations, and they show no bias between large states and small states. So it's just a little more random. Somebody might get an extra seat sometimes, but it's not always the large state that gets the extra seat. It's not always the small state. So that seems like a vast improvement, even though it's not perfect. But it was surprisingly short-lived in the House of Representatives. We replaced it in 1931 with the Huntington Hill method, which is still the method that we use today. Given how similar Huntington Hill is to Webster's method, it's no surprise that it also tends to produce apportionments that are pretty close to the standard quotas. It also occasionally produces quota violations, upper and lower, but there is no bias. So it appears that Hamilton's method is the only one of the 5 that does not produce quota violations. So that's what Max was just asking me. What happened to Hamilton's method, right? Is a big pro for Hamilton's method that it never has quota violations. So why shouldn't we just use that one? So Hamilton's method, it turns out, has 3 really big flaws. And we're going to do 3 examples here to demonstrate each of those 3 flaws. So let's say we have a small country, Calavos, and it's got 3 states, Bama, Tecos, and Illinois. Total population of 20,000. There's 200 seats in the House of Representatives. We want to apportion the seats using Hamilton's method. So let's start like we always do by finding the standard divisor. Total population divided by the number of seats. 20,000 divided by 200. 200. It's 100. Yes. Yes. 1% of the whole population is in the House of Representatives. Okay, so we calculate our standard quotas by dividing each state's population by our standard divisor. This is nice because I can do it in my head, dividing by 100, just move the decimal to the left, so I get 9.4, 90.3, and 100.3. 3. Add those up, and I should get 200 seats. And I do. Then I give every state their lower quota, which means round everything down, 9, 90, 100. And that adds up to 199 seats. I have one surplus seat. Who gets it? Bama. Yeah, why Bama? Yeah, because the decimal part is 0.4, which is the biggest decimal part of any of the states. So my final apportionment, I'm going to give my one extra seat to Bama. They get 10, and then Tecos gets 90, and Illinois gets 100. So I end up giving out 200 seats. Okay? All right, so let's see what happens now. Now imagine that overnight, the number of seats increases to 201. We're going to have one more seat in the House of Representatives. I want to recalculate the apportionment using the new number of seats. Again, Hamilton's method. So my standard divisor is now 20,000 divided by 201. So now I'm going to need a calculator because this is not going to be as nice. Okay. Did I do it wrong? 99.5, 99.5. We'll just call it that. Okay. All right, so then I take each state's population, divide by 99.5 to get the standard quota. So 940 divided by 99.5, 9.447. 90/30 divided by 99.5, 90.75. And 10,030 divided by 99.5, 100.8. If I add those up, it should come out really close to what? 201. If it doesn't come out to 201, why is it really close and not exact? Yeah, I rounded these three numbers to the nearest tenth or hundredths. Like, so if it doesn't come out to exactly 201, it's just because you did some rounding. All right, next step in Hamilton's method is round all these numbers down. So I have 9, 90, 100. So that adds up to 199. I have how many extra seats to give out now? 2. Okay, who gets them? Tecos and Illinois have the largest decimal pieces. So Illinois gets 101, Tecos gets 91, and Bama gets 9. All right. Try to put yourself in the shoes of Bama. What are your thoughts here? Yeah, when there were 200 seats to give out, you got 10 seats. Now there's more things to share, right? There are more seats to go around, but you only get 9, right? So it's like, if you think of it in terms of the mom with the kids and the candy, right? If there's more candy to give out and one of the kids is now getting less candy, they're going to be really mad, right? All right, so Bama is thinking this is unfair. It changed a lot in US history. We have now permanently set it at 435, but it's totally dependent on the people running things. Yeah. So the result we just saw is called the Alabama paradox, and it happens when an increase in the number of seats to be apportioned causes a state to lose a seat. Okay, the name comes from the 1882 apportionment of the House of Representatives. Here's a summary of what was being debated. We have Alabama, Texas, and Illinois. If we have 299 seats versus having 300 seats in the House of Representatives. So Alabama, with only 299 seats, was getting 8, When you increase the number of seats to 300, their apportionment went down to 7. So this is a really, really big debate about the constitutionality of Hamilton's method. All right, so that's one drawback, the Alabama paradox. Let's look at another example that will show us another one. All right, in the year 2525, the 5 planets in the Utopia galaxy finally signed a peace treaty and agreed to form an intergalactic federation governed by an intergalactic Congress that has 50 seats. So this is the story of the 2 apportionments that broke up the federation. All right, so we have 900 total people living in the galaxy, and there's 50 seats in the Congress, right? So let's apportion those 50 seats using Hamilton's method. So standard divisor, total population divided by the number of seats, that should be 18. Okay. Take each population and divide by the standard divisor. 150 divided by 18, 8.3 repeating, 78 divided by 18, 4.33, 173 divided by 18, 9.611, 11.33, 16.388. Okay. So if we add those up, it should come out to 50 seats or super close to it if you rounded your decimals a little bit. Give each state its lower quota, 8, 4, 9, 11, and 16. Add those up. So that's 12 plus 9 is 21, 32, 42 plus 6 is 48 seats. All right, so I have 2 extra seats to give out. Who gets them? Connie and Elysium, yes. Those are the 2 largest decimal pieces, the 2 largest residues. So they get the extra seats. Everybody else just gets their original lower quota. And that adds up to 50. All right, everybody's happy. This is a peaceful federation. Let's see what happens after 10 years of peace. Okay, 10 years of peace, everybody's happy. The intergalactic census of 2535 shows some minor changes in the planet's population. Some people have moved. We're going to calculate the apportionment under Hamilton's method now. So I have the old population and the new population. We're going to redo the apportionment based on the new populations. Make sure that our apportionment reflects the current populations of the countries. All right, so let's see, my standard divisor is now 909, which is my total population, divided by still 50 seats to apportion. And I get 18.18. So I divide each state's population, their new populations, by 18.18. All right, 8.25. 4.29. 9.956. $11.22. 296 divided by 18.18. 16.28. Okay. So when I add those up, I should get 50 or very close to 50 because I did do some rounding. Next step in Hamilton's method is round everybody down. Everybody gets their lower quota. And then I add those up. So I have 12, 21, 32, 48. Did I do it right? 48. Okay. So I have 2 seats left to give out. Who gets them? Connie. Beta. Yeah, 2.29 is the next largest decimal place. So everybody else just gets their lower quota. And we've given out now 50 seats. All right. Let's jot down what the old apportionment was. Right? So it was 8, 4, 10, 11, 17. So I'm just going to put that underneath 8, 4, 10, 11, 17. This is the old 25, 25 apportionment. Okay. All right. What do you think? Who's that? Beta and Elysium. Okay, so beta or beta, I don't know how to say that. Their population stayed exactly the same, right? 70, they had 78 people, they still have 78 people, and they lost a seat. Okay, so they might be upset by this result. Yep, they have less representation now. Who else might be upset by this? Oh, sorry, they gained a seat. They gained a seat. They had 4, now they have 5. So beta is like, that's cool, we'll take another seat, right? Who might be upset though? Connie's population went up, right? But they didn't get any more representation. So they're like, why did beta get another seat when their population stayed the same? Our population went up and we have the same seats as before. Who else might be upset? Elysium, their population went up 295 to 296, but they lost a seat, right? They had 17 and now they only have 16. Okay, so they probably are the most angry, right? Elysium's population went up, but they lost representation, right? They lost a seat. And this is called the population paradox that can sometimes happen with Hamilton's method. It happens when a state's population goes up, but the number of seats it is apportioned goes down. A very unfair result. All right, so that's 2 paradoxes so far. Alabama population. So there's one more. For a change of pace, we're going to use a non-political apportionment problem here. We have a garbage company that serves Northtown and Southtown, and they have 100 garbage trucks. So how many trucks should they send to each town based on the populations? Okay, so let's see. We've got Northtown, Southtown, total. And we'll put in their populations, their standard quotas, their lower quotas, and then the final apportionment. So Northtown, they said, is 10,450 homes, and Southtown has 89,550 homes. So in total, that makes what? 100,000 people or homes that we have to send trucks to. All right, so the first thing we do here is the standard divisor. Right, so my standard divisor is always my total population, 100,000 in this case, divided by 100 trucks that I have to divvy up. So that comes out to 1,000. And my units on there would be homes per truck. So for every 1,000 homes in a town, we send a truck there for garbage collection. So you go to each town's population, divide by 1,000. This is nice because I can do it in my head. Just move the decimal 3 to the left. and I get 10.45 trucks to Northtown and 89.55 trucks to Southtown. That's exactly 100 trucks. But you can't send a piece of a truck to a town, right? So we round everything down and we send 10 trucks to Northtown, 89 to Southtown. But that's only 99 trucks. Where should I send the last truck? Southtown, because 0.55 is the larger residue. Okay. So we're going to end up sending 90 trucks to Southtown, 10 to Northtown. That's 100 trucks. All right, so let's say that the garbage company, they've been doing a really good job in Northtown and Southtown, and so Easttown decides to hire the same company. They have 5,250 homes. So to accommodate the new town, the garbage company says, okay, we're going to buy 5 new trucks so that we won't interrupt service to the other 2 towns. Let's carry out Hamilton's method with an additional town and 5 additional trucks. Okay, so I now have Northtown, Southtown, and Easttown in a total. And then we're going to put in their populations, their standard quotas, lower quotas, and final apportionment. So it was 10,450, 89,550, and then my East town now has 5,250 homes, and that makes a total of 100,000, 105,250. All right, so I calculate my standard divisor, 105,250 divided by, I now have how many trucks to divvy up? 105. I had 100 and I bought 5 new ones to accommodate this new town. So I divide by 105. Okay, so I get 1,002.38. My new standard divisor, divide each town's population by the new standard divisor. So I can no longer do this in my head. $10.425. $89.337. And 5.238. Yes. All right, so I add those up and I should get really close to 105 trucks. Give everybody their lower quota, 10, 89, and 5. And that adds up to 104. Okay, who gets the 1 extra truck? Which town should I send it to? Northtown. So Northtown now gets 11 trucks. Southtown gets 89. And Easttown gets 5. Which is what we originally planned, to send 5 to Easttown, right? That we bought 5 new trucks to cover Easttown. But what weird thing happened? Southtown lost a truck. We ended up redirecting a truck from Southtown to Northtown, even though their populations didn't change at all. The only thing that happened was we added a new town that got their fair share of trucks, which was 5. So let's see, Southtown lost a truck. Northtown gained a truck. Easttown got its fair share of 5 trucks. So this is weird. Weird result. Uh-oh, what's happening? Okay, so this result is called the new states paradox. It happens when we add a new state, give them their fair share of seats, and that affects the apportionment of other states. Seems like when you add a new state and give them their fair share of seats, the other states should still have the same number they had before. Yeah.
Would there be like another violation where like, I don't know, you have like one extra like truck or something, and like all the other ones are like 0.33, 0.33, like.
Oh, like who do you give the extra to if everybody has the same decimal? Yeah, that is a problem too. I hadn't really thought about that. That would be a big problem. It's bound to happen at some point. Yeah. Good question. That's another drawback for sure. All right, so to summarize chapter 4, we have 5 methods. I've got them all listed here. Hamilton, Jefferson, Adams, Webster's, and Huntington Hill. We have quota rule violations. Hamilton's method never violates the quota rule. That was a big pro in its column. All the other ones can sometimes violate the quota rule. But at least with Webster's and Huntington Hill, it was unbiased, right? But then we look at paradoxes, right? And we say, well, Jefferson's, Adams, Webster's, and Huntington Hill, they never have these weird paradoxes, but Hamilton's had all 3, the Alabama paradox, the population paradox, and the new states paradox. Hamilton's method, it turns out, favors large states. So does Jefferson's. Adams' method favors small states. And then Webster's and Huntington Hill are neutral in terms of their favoritism. So it turns out that any apportionment method that doesn't violate the quota rule will produce these strange paradoxes, and any paradox-free method will always violate the quota rule. So this is called Belinsky and Young's impossibility theorem. Very similar to the impossibility theorem we studied in terms of voting, right? That there just is no perfect way to do this. There are no perfect solutions to the problem of apportionment. All right, so here's the mnemonic to remember the methods. Again, though you will always have, there's a sheet at the front of your packet that reminds you what all these are that you can have on the test. But Hamilton's method, there's always extra ham to give out. You have to dole out the extra seats after. Jefferson's method, the J looks like an arrow pointing down, so it's a round down method. Adams' method, the A looks like an arrow pointing up, so it's a round up. Webster's, the W points both up and down, so you round conventionally. And Huntington Hill, you say, what the hill kind of rounding rule is that? Right? Because it's the one where you have to do the geometric mean and compare it, and you're like, that's crazy. Right? All right, so that's it for the lecture portion of the class. I'm going to have you start your group work, and then I'll come around and help. And if we finish a little bit early, I can walk us through some of the Excel stuff if anyone has specific questions about the project.